Hi, I'm John Siau, Vice President and Director of Engineering of Benchmark Media Systems, and today I'm going to tear down a Benchmark AHB2 power amplifier and show you the various subsystems inside the amplifier. So the first thing I'm going to do is I'm going to take off the faceplate. On the faceplate we have a little circuit board. This is connected to the control system. There's a set of lights for the right channel, a set of lights for the left channel. There's a clipped light. There's a temperature light, which is also serves a dual purpose as an overcurrent warning light. So when you hit close to maximum current, that light will flash. If you hit maximum current and clip the amplifier, both the temp light and the clip light will flash. If the clip light doesn't flash, you haven't actually reached clipping. It's just a maximum current warning light. And then there's a mute light that tells you that the channel is muted. So now let's tear it apart. There's our top cover. And here's our first magnetic shield plate. Okay, and now we have the power supply. This is a switch mode power supply, so instead of having a large toroidal transformer, and for the size of this power amplifier we need a transformer that's as big as the entire power amplifier if it was a linear supply. What we have is a tightly regulated switching supply. Gives us voltage rails that stay constant. These are actually the transformers, and you can see how small they are. Instead of having a big toroid, we've got these small high-frequency toroids. As you go up in frequency, the transformers can get smaller, and correspondingly the stray magnetic fields get a lot smaller. Not only that, but the stray magnetic fields are outside of the audio band. They're well above the audio band, well above any frequencies where they would interfere with the audio. We also have right here the input filter. So that's a line input filter. It serves two purposes. It keeps external noise from coming into the power supply, and it also keeps power supply noise from going out on the AC line. This is a heat sink, and this is also a heat sink for the power devices on the power supply. These two plates here on each side are heat spreader plates that conduct that heat out to the heat sinks. The entire AHB2 is passively cooled. It's also designed so that we have a uniform temperature distribution across the entire heat sink. There's no hot spots on the heat sink. It will generally heat up very uniformly, but the amplifier itself runs very cool. You can see some thermal paste on here, which helps conduct the heat out to the heat sinks. So there's one spreader plate. There's the other one. There's a power entry cord here, which I'll unplug and lift the power supply out so we can get a good look at the input filter, the transformers, and capacitors. One thing you'll notice is that because this is a tightly regulated supply that is able to deliver power on demand, we don't need a large bank of storage capacitors. So most power supplies for a power amplifier would have a large number of very large capacitors, at least as large as these, to store charge to try to maintain a constant DC voltage. What we do instead is supply current on demand to keep the voltages steady under varying load. And that's much more effective than a bank of storage capacitors. All right, so now we're down to the second magnetic shield plate. We've only got an inch between the power supply and the amplifier board. But if you look at the output of an AHB2 on a spectrum analyzer, you'll see no traces of 60 hertz hum, no traces of 180 hertz, which is a third harmonic of the AC line frequency. That's one of the major advantages of having a switch mode power supply instead of a linear supply. If we had a linear supply this close to the power amplifier board, we'd have all sorts of hum from the AC power line in the amplifier board, because it's very, very difficult to shield against magnetic fields, and we have to use this very special mu metal shielding to do the final little bit of shielding for the magnetic fields that we do have. Now I'm going to take these standoffs off. You can see just how heavy that plate is. All right, so now we get to some of the real interesting stuff. First thing I'll point out is over on this side and over on this side, there's two thermal sensors that are attached to the heat sinks. So this senses the left and right heat sink temperatures. We've got an FPGA right here, which is a programmable logic device that is the control center of the entire unit. It's controlling the power supply, it's monitoring output current, it's monitoring output voltage, it's monitoring temperature in multiple places on the unit. It's measuring whether or not we're in the safe operating area. So all of these things are happening at a very high rate of speed, and it's also controlling muting of the amplifier and triggering of the protection circuits. These are relays, which are in the line level input stage. They're not in the output stage. These relays switch between stereo and mono mode, and they also switch between the three gain settings. So we have one low gain setting, which is intended for studio level input signals on XLR connectors, and then we have a mid gain setting, which is intended for hi-fi XLR signal levels, and then we have a high gain setting, which is intended for the output of RCA unbalanced devices using our RCA unbalanced to XLR balanced adapter cables. So we can accommodate unbalanced signal levels, hi-fi signal levels, or full studio signal levels, depending on the position of the switch on the back of the unit. Then there's a set of high power resistors right here. This is where the feed-forward error correction is summed with the output of the main amplifier. That's one of the purposes of those resistors. And actually there's two identical output stages on each, both the left and the right channel each have dual banks of transistors that are summed in these output resistors. So over here we have 4 PNP transistors and 4 NPN transistors that are the push-pull of the Class AB output stage. There's a smaller amplifier in here and a smaller amplifier over here, which are the feed-forward error correction amplifiers that are passively summed over here in the summing network. The output connectors, you can see we have wires going up to the binding posts, but you'll also notice there's the speaker output connectors, which are soldered directly to the board. And because they're soldered directly to the board, we can actually monitor the voltages right at those pins, and we can give you better performance through the speak-on connectors than you have due to this extra wire for the binding posts. So if you're looking for the ultimate in performance from the AHB2, we always recommend using the speak-on connectors. The other thing about speak-on connectors, they're a high current connector. They don't loosen up when you bump the cable. If you bump the speaker cable, very often the binding post will loosen up. So down in this region of the board, we have a series of circuits that measure the output current, the output voltage. They measure the amount of distortion. So if the distortion coming out of the amplifier exceeds a certain threshold, we actually shut the amplifier down to protect your tweeters. So one of the cool things about the AHB2 is that if you overdrive it, it's actually going to shut down to protect your speakers. So maybe you had it set at the wrong gain, maybe somebody turned the volume up while the system was off. You turn the system on and it's a lot louder than you expected. Instead of burning out your speakers, the amplifier will instantaneously mute and prevent any damage. One of the other things I want to point out is all of the output devices are clipped directly to the heat sinks. And these clips, these spring clips, one of the nice things about them is they allow for thermal expansion. So there's a freedom of movement up and down and in and out that you wouldn't have if those devices were bolted to the heat sink. So for long-term reliability, these spring clips have significant advantages. The circuit board in the AHB2, both of the circuit boards are actually 6-layer circuit boards. One of the things that we do in the amplifier board is we actually use star quad distribution of power supply rails and audio signals so that they are immune to magnetic interference. And so we have a pair of traces and a pair of traces where this trace and this trace are connected together and this trace and this trace are connected together. And now the geometric center of that, no matter which side you look at it, the magnetic fields are perfectly centered. And so that cancels out the magnetic fields that would have been caused by those traces if those traces are high current traces. If they're low current signal traces, it means that we get exactly the same amount of interference on both the plus lead and the minus lead, and that can get taken out by a differential amplifier. So we build the board to have high magnetic immunity, and also on the high current traces, we're designing those to have magnetic fields, stray magnetic fields that cancel each other out, so that we're not radiating magnetic fields that could interfere with other parts of the circuit. One of the cool things about the AHB2 is that you can stack a preamplifier directly on top of it. You can stack a DAC directly on top of it. You can stack another AHB2 on top of it. You can even take a microphone preamplifier and put it directly on top of the AHB2 without having interference from the power supply. That's very unique among power amplifiers. Most power amplifiers, you don't want to have your preamplifier anywhere near the top of the or bottom of the chassis. But because we're using these high frequency transformers, the magnetic fields are very small, very well contained, and I should point out that these toroidal coils are fully encased in ferrite, what are called pot cores. That greatly reduces the stray magnetic fields And these magnetic fields are on the order of 500 kilohertz. They're above the bandwidth of the amplifier and easily filtered out without interfering with the audio signals. One of the other things I want to point out about the amplifier is that there's no relay in series with the speakers. The speakers are connected directly to the power output devices, and there's a low noise mute circuit that mutes those output devices, and we actually shut the power down to those output devices so that in the event of a failure of any of the output devices, so that under no circumstances do we put out damaging voltages into the speakers. So getting that relay out of the signal path is really important, because relay contacts are notoriously bad as far as creating distortion in speaker outputs, and that gets worse over time. Every time you turn the amplifier on, turn it off, those contacts are opening and closing, and the contact resistance is increasing. And by getting that high power relay out of the signal path, as we've done with the AHB2, we don't have that degradation in performance over time. One of the other things I point out on this amplifier is there are no adjustments on the amplifier board. So there's no trimmer pot for bias voltage. That's quite unique in a power amplifier. And one of the reasons for that is we're able to underbias the amplifier because of the feed-forward error correction. So biasing is non-critical, and we've also done some things to keep the bias carefully controlled. The other thing that we do is we use very high precision components so that we don't have to trim things like common mode rejection on our balanced input amplifiers. That's all trimmed with precision 0.01% resistors instead of using trim pots. So that concludes the teardown of the AHB2. I hope you've been able to see that it's quite a bit different than a lot of power amplifiers, particularly traditional power amplifiers where we'd have big toroidal transformer. This is a very different structure and designed for ultra high performance, designed to have a 500 kilohertz bandwidth. The AHB2 has a 135 dB signal to noise ratio, and we could never do that if we had a linear power supply. So the switch mode power supply is a very key component to achieving ultra high performance. Thanks for joining us.